Good morning, good afternoon, good evening, depending on your time zone out there. I'm Rach Weston. I'm product manager of analytical products here at Gatan, and I'd like to welcome you to the first in a series of webinars on some of the new features that we've added to Gatan Microscopy Suite, GMS 3.4. Our speaker today is Dr. Liam Spillane, and Liam, when he's not out on the slopes promoting eels, he's in various labs promoting eels. He's one of our application scientists here at Gatan. He's done a lot of work both on the development of our techniques and also the training and promotion of the techniques. So Liam will be presenting today. So if you have any questions, we have the ability to get to your questions right away if they're related to the connectivity of the system. But if you have questions related to the actual presentation, we'll save all those questions till the very end, and then we'll put those all together into one set. Okay, so without any further ado, let's welcome Liam to talk to us about how to use the new features of quantitative EELS mapping for phase analysis. All right, thank you.
Okay, thanks, Ray. And I'd like to thank everyone also for signing up and tuning into the first of the Analytical webinar series. So model-based EELS quantification and ELNES phase mapping. So just a brief overview of the presentation. So we're going to cover some background and theory at the beginning. So EELS quantification and fundamentals, the model-based approach, how we do quantification in GMS3, and then the new standards-based approach and ELNES phase mapping. And then in the second half of the talk, I'm going to draw on some application examples. So we have two primary examples. One is a semiconductor device, so we'll be looking at high energy edges, so silicon K, tantalum M, tungsten M. And then the second application example, I'm looking at a functional oxide, so an oxide of barium, strontium, cobalt, and iron. So what's the fundamental aim of elemental quantification? So we want to identify, extract, and quantify element-specific information from the energy loss spectrum and convert to meaningful analytical quantities. So as we all know, ionization edges in the EELS spectrum provide element-specific information. So the presence of an edge tells us what there is, so it's good for element identification. The relative size of the edge tells us how much of that element there is. The shape of the edge, so the near edge fine structure, tells us about the chemistry and the bonding, and post-edge modulations tell us about nearest neighbor information. So for quantification, we're interested in two primary parts of the spectrum. So we break it down into background intensity. So this isn't proportional to the elemental signal, but we need to account for the background when we're fitting. And then the ionization edge intensity. So the ionization edge intensity is proportional to the elemental concentration. So the next thing we need to ask ourselves is how do we go from something that's just some scattering intensity to something that's a meaningful analytical quantity? So the probability of inelastic scattering into a core loss edge, so P sub K, is a product of the projected areal density, so the number of atoms in the beam path, and the inelastic scattering cross-section. P sub K can also be measured by taking the extracted edge count integral and dividing by the total number of counts in the spectrum. So we end up with two fairly simple equations. So if we equate these two, we end up with something where we can do quantification in terms of something that we can measure in experiments. So two intensities, scattering cross-section give us our areal density. So this is our absolute quantification equation. We can also do relative quantification, so concentration of A relative to concentration of B. And this is essentially the same equation, so it's just flipped over, one divided by the other, so the zero loss integrals cancel here. So I've mentioned a lot about these scattering cross-sections. So what do we mean by scattering cross-section? So just a little recap, this is the double differential equation for EELS. So we're really interested in how the inelastic scattering intensity varies with scattering angle and varies with energy loss. So we have three kind of main parts to this equation. We have a scaling term, which is just constants at the beginning, an angular term, and an atom-specific term. So the cross-section decreases with higher energy loss and accelerating voltage. The angular distribution follows a Lorentzian distribution approximately. And since the scattering angle increases with energy loss, the angular distribution broadens with energy. DFDE is known as the generalized oscillator strength, and this is where we introduce atom-specific physics into the cross-section by the transition matrix. So in practice, cross-sections are computed for specific experimental conditions, so beam energy, collection angle, convergence angle, and that calculation is done in software. So typically it's done in the EELS quantification plugin in Digital Micrograph. We have various cross-section models. The most commonly used cross-section model is a Hartree-Slater cross-section model. So again, in practice, what's the significance here? So the cross-section is essentially a theoretical model for the edge shape. It's a single atom scattering model, so there's no solid state effects, i.e. it doesn't account for the near edge fine structure. It just gives us the basic edge shape. So here's an example of a calculated Hartree-Slater cross-section for lithium. So it has this characteristic sawtooth basic shape, which K edges tend to have. So model fitting quantification in GMS3, we are fitting signals by model fitting. So we need to identify the core loss edge or edges present in the spectrum, create fit models. So the first fit model is a background model. So it's typically a power law with the exponent determined from this pre-edge fit region. And then the second fit model is the computed cross-section. So this is what I was talking about with these Hartree-Slater cross-section shapes. So the fit models are fitted simultaneously to a single fit region using multilinear least squares fitting. So we have a pre-edge region of 5 eV, and by default, the ELNES is excluded to improve accuracy. So this procedure will be repeated for every edge group, and the edge results are combined for quantification. So here we have a relative quantification example for boron nitride. So as we'd expect, we have a one-to-one approximate ratio between the boron and the nitrogen in boron nitride. So what's the benefits of model fitting quantification? So the fact that we are doing model fitting in itself is the primary benefit. And then most of the other benefits stem from the fact that we're fitting models. So we can account for overlapping edges. We're able to do plural scattering correction, and we're able to exclude the ELNES. So let's just take a step back and recall how we used to do quantification. So we used to do background extrapolation, and it's important to kind of get across that we're not doing that anymore. So the old approach involved fitting multiple windows. So we had a background window per edge for the background, a signal window for the edge signal. We then extract the signal and quantify using the quantification equations. So two kind of big drawbacks here: not able to accommodate overlapping edges. So the reason that we can't accommodate overlapping edges in this background extrapolation method is that we always have to have some pre-edge background. And if our edges are overlapping, we just don't have a sufficient window size here to actually fit a background. We also can't deal with plural scattering in this old background extrapolation method. Okay, so let's kind of touch on those two individually. So first of all, quantification of overlapping edges. How does that work in GMS3? So first of all, the model-based quantification can separate edge overlaps, which is, you know, a big step beyond background extrapolation. The way that's done, essentially you have a single background and multiple edges in a single fit window. So instead of having to try and fit a small background window here, we just have one big background that's projected under both edges, and then we could do this multilinear least squares fit over the whole region. So the software will automatically determine if these edges are overlapping, and it's really particularly effective for EELS spectrum image mapping. So plural scattering, so let's just recap what is plural scattering. So plural scattering causes a redistribution of the core loss intensity. So essentially we'd start off with single scattering distribution, ionization edge, and what we end up with in our real experiment is a convolution of the low loss scattering with our ionization edge. So why is that important to us? So it changes the edge shape and intensity. So the primary reason that's important in quantification is it invalidates the computed cross-section, so the shape becomes wrong. So how do we deal with that? So background extrapolation method, so the old method. So there is no plural scattering correction here. So it's actually necessary to remove the plural scattering from the data set itself before doing quantification. So that would be done with a Fourier log deconvolution or a Fourier ratio deconvolution. So there's one big disadvantage in doing that. And in doing these deconvolutions, you actually have a noise amplification effect. So we are making our data worse. Model fitting. So we go the other way around in model fitting. So we actually incorporate the plural scattering into the fit model itself. So we do a forward convolution of the low loss and the Hartree-Slater model. So the advantage here, before anything else is considered, is that we have a noise smoothing effect instead of a noise amplifying effect. So what other benefits are there? Well, we need to look at some data for that. So here again, we'll draw on the boron nitride example. So what we're looking at now is the data without plural scattering correction. So we have the background shapes and then the basic edge shape for the K edges. So we have these sawtooth cross-section shapes. So it's just a single button click in the edge setup menu. You just activate this guy, include plural scattering. We do need the low loss, so it's pretty much you need to have a dual EELS data set. When that is enabled, you can see how these basic cross-section shapes are modified quite considerably, and they then fit the raw data much more accurately. So the fit becomes better, and when we're doing this model-based quantification, the fit quality really is a measure of how good and how accurate the quantification is. So anything that we do to improve the fit is going to help us. So again, exclude ELNES. So the ELNES is not accurately described by the cross-section models. So by default, in the model fitting method, we exclude the ELNES region from the quant fit because we know we shouldn't try and fit something in an area where it doesn't fit, in essence. So the top example here, again, boron nitride. We're looking at the nitrogen K edge with the ELNES region excluded. So you can see in this high energy loss part of the spectrum, the fit is very good. Without the ELNES excluded, the fit is worse. So as you can see, the quality of the fit is what we're really kind of interested in model fitting quantification. So you can imagine that the limitations of model fitting quantification relate to how well we can fit. So model accuracy and tightly overlapping edges is another example. So another two examples. So we'll touch again on ELNES. So remember, the fine structure is not modeled by simple atomic models. So we need to exclude for the best fit. So this is an example for the oxygen K edge. So our fit's better in the high energy loss region of the spectrum, but we're actually throwing away chemical and bonding information, and we're reducing our signal. So both of those things, not good. Cross-section accuracy. So not all ionization edges have ideal cross-section shapes. So here's an example for tantalum. So this is the tantalum M edge. So you can see again, the cross-section shape here doesn't fit the actual experimental spectrum super well. So if we have a non-ideal fit, it limits the accuracy of quantification. Final example, tightly overlapping edges. So model-based quantification can separate overlapping edges, but if there's too much overlap, the algorithm is going to struggle. So a good example is this functional oxide that I'll be talking about later. So we have barium and cobalt in the sample. So we have an M edge at 781 EV and an L edge at 779 EV. So the problem here is that these two signals differ really only in the near edge fine structure region. And that's actually what we're excluding in the model-based fitting. So, we need to do something else to deal with this, this kind of sample, but more on that later. So that kind of leads us to ask the question, how can the model-based approach be improved? Okay, and that's where standards-based quantification comes in. So standards-based quantification is essentially an extension of model fitting. So we use the shape of an experimentally measured edge for fitting over the ELNES region. But we still use a Hartree-Slater cross-section to fit in the non-ELNES region. This gives us a much improved fit model, and if we can fit better, as I've already said, our quantification gets better. So we'll look at this in a little bit more detail. So what we're doing is, so for boron here, we have this measured standard. We define an energy range for the standard. So that's where this blue dashed line is. So that's where the experimental part ends. And then we have a Hartree-Slater cross-section shape above this kind of energy. So what's happening is this experimental edge shape is getting spliced and scaled with a theoretical cross-section for the specific experimental conditions of the data. So what this is allowing us to do is, kind of go and calculate the areal density, the atomic concentration, the volumetric density. One thing that's advantageous is that we can deal with plural scattering. So plural scattering can be removed from the experimental measured standard if we have dual EELS. And this allows us to do thickness compensation later when we're using this standard for quantification. So that's really powerful. Again, that's in one of the examples later. So it's managed in software with a standards database. So essentially we store and manage a standards library. So this is the interface. So you can populate this with a bunch of standards, then search by element, beam energy, plural scattering, for example. So what are the benefits of standards-based quantification? So we can include the ELNES now. So this gives us an improved fit, more accurate quantification results. We have more signal, so it's going to improve our signal-to-noise ratio, have impact on detection limits, and so on. We can deal with tightly overlapping edges. So this is something that was impossible for conventional EELS quant approaches. So we can now do something that we couldn't do before. ELNES phase mapping, so also impossible for conventional EELS quantification. So what we're able to do now is we're able to do a similar kind of fit to linear least squares fitting using experimental references, but in a more robust and capable manner. So we get quantitative results, so areal density, volumetric density, percentage composition, instead of just fit coefficients. We're also able to deal with plural scattering. So this allows us to correctly handle thickness effects. So let's start off with the first application example, so the semiconductor. So this is an example of the workflow that we call internal standards. So internal standards are where we're taking the standards from the data itself. So it's simple, fast. The dispersion, energy scale, anything optical, aberrations is internally consistent because the reference is taken from the data set itself. We don't need to worry about calibration mismatches or things like that. The downside is it has limited use. So this is only applicable where the phases are well separated. So the workflow is as follows. We start off, acquire the spectrum image data, then we measure the standards, perform the edge setup, and then we go on and do our quantification and mapping. Okay, so I'll jump over to digital micrograph here and show you an example with the actual data itself. So we're looking here at spectrum image data set. So we have ADF here in the top left, low loss data set, and a high loss data set. So the first thing that we want to do is use a spectrum picker tool, which I've already have open here, to extract spectral data from the spectrum. So I'm interested in tantalum, tungsten, and silicon. We actually have a whole bunch of other elements here. So to measure a standard, you need to, first of all, add add an edge to the edge list up here in elemental quantification. So we can do that with a periodic table. So we can see that I've already added tantalum, tungsten, silicon. Then we select one of these signals that you want to measure a standard from. So I'll select silicon. And then we have this new function at the bottom here. So we expand with this little triangle, and then you hit measure. So the first thing that happens is we need to extract the signal here, the silicon signal. So we need to define a background window. So we draw a good background window. Once we're happy with the background placement, hit OK here. Now the software looks to see if this is part of a dual EELS data set. The software has identified that there is a child low loss data set here. So it asks us if we want to perform deconvolution. So this is always, if you can do this, this is beneficial. So this is why I like to sum over a large group of pixels. So it increases the signal to noise ratio, and it'll offset the kind of the noise hit that we have when we do the deconvolution. So then we press yes. And the last thing that we have to do is the standard setup. So, oops, press the button a little quick there. So let's do that again. So, okay, yes. Okay, so we just need to give the samples, the standard, some sensible name, write in some notes. We can choose to keep for this session only, or actually if we uncheck that, it will write to the standards library permanently. And then looking up here in the top left, you have the standards. So the last thing that we need to do is just define the range here. So you can see if I change the range here, it just increases the size of this. Basically, we're defining where the splice point is when we do that. So we choose where the splice point should be. We just want the splice point to be somewhere where that Hartree-Slater cross-section model starts to look good. So, okay. And then we would do the same thing for tungsten. So it's important here that I'm looking at a region where I know that it's silicon in this oxide phase that we're interested in. Then we can do the same thing for tungsten. Measure. Okay, yes. Tungsten demo 2. So this one is where it's important that we're only in a tungsten region, because we don't want to be basically overlapping these signals and getting some weird mixed standard. So just make sure that we're in this tungsten only area. Hit OK. Do the same thing for tantalum. The tantalum is actually this thin strip here. So we put our picker tool in the pure tantalum area. Choose the tantalum, hit measure. OK. Do you wish to perform the deconvolution? Yes. So you basically just build these library of standards. Okay, so once we've imported the standards, then we just do the quantification as we would normally do. So you select the high loss spectrum, and then we enter the edge setup. Now, because we have standards, the thing that you'll see that's primarily different is we have standard here as a choice, a cross-section choice. So it was Hartree-Slater, and now standard is available. So if you want to change the standard, you hit this little button, and that's how we access the standards library. So let's do that. Okay. And then we just hit map. So hit OK and generate some maps. And then we end up with a nice silicon, tantalum, and tungsten map. So the results for this sample are actually in the presentation. So we'll jump back to the presentation, the slideshow, and continue. So, okay, so model-based results versus standards results. So as I've already said, in some cases, the model-based method can't deal with overlap. So the two primary kind of categories that we have here are where we have tightly overlapping edge groups, or where the theoretical cross-section models don't correctly represent the ELNES. So here we're looking at the second example where our cross-section models don't correctly represent the ELNES. So same sample, so the semiconductor. So here we're looking at spectral data that's extracted from the silicon oxide region. So if we overlay the models here, you can see that the K-edge cross-section shape fits the silicon K-edge pretty well. If we do the same thing in the tantalum layer, it's not the same story. So you can see that the tantalum cross-section shape is this orange shape here, and it doesn't fit the data very well. So what actually happens is the fitting algorithm can get a better fit by adding in some tungsten. So what does that look like in the maps? So the silicon map looks okay. The tantalum map is good, so we know that this region is a tantalum layer. In the tungsten region, we have these tungsten plugs, which are tungsten, strong contrast in the map, but we have this blue kind of stripe here, which is coincident with this tantalum layer, and this is purely an artifact. So this is just because the fitting algorithm can get a better fit by adding in a tungsten shape. So experimental standards provide a much more accurate fit. So if we do the same thing again, so with experimental standards, we have our measured standards. So this would be the tantalum shape, tungsten shape, silicon K shape. And then if we look at the fit with actually a measured tantalum shape, you can see the fit is now very good. So the effect in the map, that artifact is no longer present in the tungsten map. So that's a big advantage for us. So, okay. So the second application example, this is the functional oxide. So this work's been completed in collaboration with the Laboratory for In Situ Nanomaterials Characterization with Electrons. So this is a group based out of EPFL, Lausanne, Switzerland, led by Professor Tillaley. So I'd like to thank Professor Tillaley for involving me in this project. I'd also like to thank Sue Shen, one of her Ph.D. students, for doing some of the data acquisition. So Sue Shen acquired the spectrum image data from cobalt oxide, lithium cobalt oxide, and the BSCF sample. And then Renis, another PhD student in the group, has done a bunch of fine structural calculations using density functional theory and charge transfer multiplet code. So what's the background here? So it's an energy storage problem or solution, depending on how you look at it. So water electrolysis to store hydrogen is a weight-efficient and location-flexible method to convert and store surplus electricity. So around 45 million tons a year of hydrogen are produced for industrial applications, such as fertilizer production, petrochemistry, as a process gas for semiconductor fabrication, chemical synthesis in the food industry, metallurgy, and the glass industry. So this is a heavily used material. So as you can imagine, there's a considerable interest in optimizing its manufacture. So there's considerable interest in development of catalysts for the anodic oxygen evolution reaction in water electrolyzers. So cobalt-based oxides in particular show high tunability of their functional properties due to the possibility of cation substitution in the oxide during synthesis. So BSCF is a really good electrocatalyst in alkaline solution. It has a complex perovskite structure in bulk, but when we're talking about catalysis, we're really interested in the surface properties as they're key to the functional behavior of a catalyst. So what we're interested in is what is the origin of the high OER activity of BSCF. So the experimental aims are to first acquire cobalt-2 and cobalt-3 references. We want to validate the ELNES phase mapping and concurrent standards method on a known material. So the known material is CO304. So it's a mixed valence cobalt oxide. We're using a Titan Themis and GIF Quantum. So that's the system at EPFL. So 300 kV, 100 millieV per channel, and dual EELS. And then the other experiments are completed on a Joule F200 and GIF Continuum ER at Pleasanton in California. So all the work on the Joule was done at 200 kV and a 300 millieV per channel dispersion, and the energy offsets for the two data sets are the same. So we want to perform ELNES phase mapping to characterize iron, barium, and cobalt chemistry in the spent BSCF catalyst. So we start off with the method validation. So we're looking at cobaltite. So it's a normal Spinel structure, so a large cubic unit cell. And what's important here is we have cobalt 2 and cobalt 3 on tetrahedral sites. Well, cobalt 2 is on tetrahedral sites. Cobalt 3 is on octahedral sites. But it has a very well-defined cobalt 3, cobalt 2 ratio. So it's a really good test material for using concurrent standards. So what do we mean by concurrent standards? So this is the new approach where we're using multiple standards for the same ionization edge when we're doing EELS quantification. So why is that useful? It allows us to do phase separation. We can do oxidation state mapping, fine structure mapping. So there's some really nice things that we can do with this new method that we couldn't do before. So what's the workflow here? So this is what we call external standards. So this is applicable to any sample because the references are taken from, materials that we are happy with. So we're only limited here by the quality of the references. Downside is that this is more time intensive than internal standards. There's more data acquisition required. You need to think about the samples a bit carefully, and there's more processing. So the workflow here is that we acquire our reference data, then we measure the standards from the reference data, then we acquire our unknown data, then we validate the standards and the unknown data. This is quite important. It's important that the quality of the standards and the unknown data are the same. So you want the calibrations to be good in terms of absolute energy. You want the dispersion calibrations to be consistent. You want any aberrations in the two data sets to be consistent. It's also helpful if you want to do very look for very fine changes. You want the energy resolution of the two or the multiple data sets to be the same. So finally, we perform the edge setup on the unknown data, and then we do quantification or mapping. So let's jump back to digital micrograph and look at the cobalt data. So here we have 3 workspaces. So one is the cobaltite workspace, so CO304. Then we have cobalt monoxide and lithium cobalt oxide. So as you can see, these are all fairly similar. So these are all dual EELS spectrum image data sets. So the workflow here is, okay, so the first thing that we need to do, so we look at the cobalt 2 reference. So we want to acquire, use a spectrum picker tool, extract some spectral data from the high loss data set, just like we did before. We need to then add a signal in the edge list. So we have cobalt. So I added that from the periodic table here. And then we do the same thing. So once this signal is marked up on the spectrum, you hit measure. We have to do the same thing we did before. So we need to set a background, ask us if we want to remove plural scattering. So I say yes. And then we have the same thing. We have to give some sort of meaningful name and add some notes, and then define the splice point. So you really want to just cover all of the ELNES and then make sure that the Hartree-Slater cross-section then fits well at the point where you do that, make that splice. So if we hit OK, and then we would do the same thing for lithium. So I won't repeat that to save time. So once our standards are present in the standards library, then we go to our unknown data. So this is big cobalt CO304 particle, and then the spectrum image data from that particle. We will then have a spectrum extracted. This I've already done. So So we go through the same thing, right? So we have oxygen. I have a standard for oxygen, so we can see that it's a standard here. So what we're interested in here more is this concurrent method. So the way we set up the concurrent standards is you go to your cobalt signal in this case, and then we go to this setup button here. So you click this guy, and then you have this option here that says multi-selection advanced. So if I disable that just for a demonstration, so if we enable multi-selection, then whatever we have here is the first standard in the list. So I will just select the other reference, add that reference, and then hit OK. And you can see in this example that we actually have two references for cobalt. So we have one reference, which is the 2+, one reference, which is the 3+. So we can either hit quant or we can hit map. So this is all the same, so I'll hit quant. We end up with quantification results in the results window for the three references or the three signals that we're using there. So let's jump back to the presentation again. So, okay, so what are the results for this experiment? So the first thing we're looking at is the method validation, so with that mixed oxide. So this was done on the Joule, so we're looking at ADF, low loss, high loss. The relative thickness, the average relative thickness over the area that I've summed is T over lambda of 0.36, so it's quite thin. So what were the composition results? So the composition results that I got are we have 60% oxygen, around 14% cobalt-2, and around 27% cobalt-3. And we have a ratio of 34% cobalt-2 to cobalt-3, 66%. So let's just recap the same values for the stoichiometric oxide. So for stoichiometric oxide, we're expecting 57% oxygen, 14% cobalt-2, 29% cobalt-3, and a ratio of a third to two-thirds. So if we compare with what we actually measured, we are very much like on the money here. So I'd say the method has been validated. Okay, so how do we deal with plural scattering? So let's see, how robust is that? So this is the same experiment, but I'm actually looking at a different particle, so a different oxide particle. So this is a non-ideal ROI. So this particle is way thicker than the previous particle that we looked at. So in the thickest regions, we're looking at T over lambda of 2. And on the edge, the thickness is more like 0.7 lambda. So not only is this sample thick, it's also the thickness is changing a lot. So it's not really, we would probably choose not to look at this sample in a normal EELS experiment. So let's look at the results. So I'm showing some data from a region with a thickness of T over lambda, 1.55, so quite a thick region. So this is the first example with the plural scattering off. So I'm trying to fit over a pretty big energy window, so 164 eV. There's a lot of plural scattering here, but I'm using references that don't have plural scattering removed, so they're single scattering distributions. So not surprisingly, the fit is not very good. So in fact, if the fit here is so bad that it lifts the power law away from the background, the actual, the real background. So one thing that we can do is just decrease the size of the fit window. So if we go to a fit window here that's more like 85 approximately EV wide, so I'm excluding most of the plural scattering, just really fitting the two white lines of cobalt, and then the fit quality improves. So the fitting is better, but I've thrown away tons of signal, so this is not really ideal. So how about with plural scattering correction on? So if we switch on the plural scattering correction, I'm able to go back to this really big window, so the large 164 EV wide window, perfectly deal with the plural scattering, and then you can see that the fit is now very, very true to the data. Okay, so spent a lot of time on the method validation, so let's now look at the interesting sample, so the BSCF. So just to recap, this was done on the Titan. So dual EELS, 300 kV, 100 millieV per channel. So the signals that we're catching here are iron L, cobalt L, and barium M. So let's just kind of think about what would happen if we use model-based quantification. So we're unable to separate the cobalt L and the barium M. We're unable to separate the cobalt 2 and the cobalt 3. So there's limited things that we can do, to solve our materials problem using the older quantification method. This sample also has a large change in thickness. So, all of these things kind of lead us to think, it's kind of lucky that we have this new standards-based quantification method because we can deal with all three of those points. So standards-based quantification, same extracted spectrum. So we can extract the cobalt and the barium separately. So you can see that we're using a barium reference and it separates the cobalt and the barium perfectly. So the yellow is the barium and then the purple is one of our cobalt references. We can use concurrent cobalt standards. So you can see that I have 2 cobalt standards just as I did for my mixed oxide, so for the other specimen. So this is really useful. So it allows us to do everything that we would do in the regular quantification. So we get the same calculations. So we have 2D areal density maps, volumetric density maps, and atomic concentration. And we're generating this with Plural scattering correction applied. So you can see here I have 4 maps for atomic concentration. Our cobalt 2, cobalt 3, and barium are successfully separated. So what does this show for this material? So this has allowed us to get chemical profiles for all of these, these signals. So the results are showing us that there's cobalt 3+ majority in the bulk, but there's a switch to majority cobalt 2+ at the surface layer here. So you can kind of see this profile increase and this one decrease. So that's pretty key here. So the guys at EPFL, they've also done a bunch of microstructural studies on this material. So the results of the microstructural imaging show that there's a change in the surface structure from a perovskite structure to a Spillane structure. So the running hypothesis here is that this high OER activity of BSCF is believed to result from tetrahedrally coordinated cobalt 2+, kind of residing in a cobalt iron spinel surface layer on the material. So there's this kind of interesting surface properties that directly relate to the functional properties of this material. So this is something that you wouldn't be able to find out in a method other than like STEM EELS, and also using this new standards-based quantification method. So it's really powerful. Okay, so that's kind of nearly the end. So summary. So EELS quantification using standards provides us all of the benefits of model-based quantification, but with some key advantages. So we have improved fit quality, so we get more accurate quantification results, greatly improved results for edges with poor calculated cross-sections. We also can do ELNES phase mapping. So this gives us the capability to separate these tightly overlapping edge groups. We can separate phases, do oxidation state mapping using concurrent standards. So this really allows us to do true chemical mapping and not just composition analysis. And then the final advantage here is that we can do all of this with Plural scattering correction. So we have mapping options that are conventionally only really possible using MLLS fitting, but now we're able to correct for thickness effects. So this is really useful. So it allows us to kind of look at a much wider range of samples. So we can look at non-ideal samples, so things that are much thicker, and things where the thickness is changing a lot. So I'd like to thank everyone for tuning in. And if anyone has any questions, we'll try and take a few questions. So just submit any questions through the questions pane.
Thank you very much, Liam. That was very informative. Yeah, and thanks everybody for attending. Yeah, we did have quite a few questions coming in during the presentation. Was trying to get to some of them in real time. I hope I didn't typing and listening at the same time are a little bit challenging. But so we did have some questions. Probably what everyone really wants to know is when you're out there promoting eels on the slopes, are you a skier or are you a snowboarder?
Oh, I'm a snowboarder, so
Okay. Well,
hopefully that's acceptable to the masses. Maybe I'll try skiing one day, maybe.
Yeah, you millennials, I don't know. But yeah, more seriously, so when you're using a standard from another sample from your method 2, does it need to be at the same dispersion and the same settings as the data that you've acquired, or can you adjust for that?
So it doesn't need to be at the same energy, it doesn't need to be at the same dispersion. So the software, in fact, the data that I showed you, the standards were required at 100 millieV per channel. So that, and the fitting, some of the fitting I did was at 300 millieV per channel. So we can use it for different experimental conditions. So one thing that is kind of important, if you're doing very kind of like small chemical shifts and things, there's actually electron-optical aberrations that are dispersion specific. So if you want to have the best, we can't account for those electron-optical aberrations. So the best way to minimize the effect of those aberrations is if they're consistent with the data that you're fitting and the standards. And the easiest way to do that would be to use the same microscope at the same energy dispersion. Does that answer the question? Or?
Well, I think so. Yeah, I think I got it at least.
Okay.
So there was a question about using, if you don't have all the elements, can you use computed cross sections and standards at the same time?
Yes. So all that happens when you measure the standards, standard becomes one of the available choices as a cross section when you're doing the quantification. So you can still choose Hartree-Slater. So you can mix and match Hartree-Slater or hydrogenic or standard.
Okay, that makes sense. Also, can this software run on a quantum-based system, or is it specific to the new hardware?
So this isn't hardware specific. So for offline processing, it doesn't matter. For online, GMS 3.4 is currently not released for quantum, but it will be coming out for quantum in the next few months. So as soon as hardware support's enabled for quantum, then this could be done on an online system. But for now, you could, in theory, just acquire the data and then do the processing on an offline system. So essentially, if you have a full analytical license for your GMS3 quantum, you could already upgrade your offline license to GMS 3.4. You just couldn't upgrade the online. Yeah.
Okay, so for the offline, so yeah, the offline, I guess, is agnostic against the version that you have
Exactly.
filter. So related to that, I also want to point out that there's free software, offline software available on the Gatan website. And also, since there's so many people who are currently working at home and don't have access to the laboratories, we have created a version of GMS 341 for offline analysis that includes the full analytical suite. It'll run for a limited time, but it'll give everybody a chance to use this exact version of software you've been using here on their home computer, even if they don't have a license for that. So we'll follow up with an email to the group here on how to download that version. We're still working out a couple of things on the download site to make sure it works correctly. So we're running up on 8:50 here, and I've got a whole bunch of questions. So I think maybe what we should probably do is I'll try to get to these questions here offline, and we should let everybody go and get on with their morning or their afternoon. And just want to implore everybody to stay healthy, stay safe, and stay positive. Through these trying times. I think we're all going to get through it, and it's great that we can all work offline and have these sort of like webinars and things where we can still keep learning and keep moving forward. All right, I want to thank you, Liam, for your presentation, and thank everyone for their attention.
Okay, yeah, thanks very much. I look forward to hopefully everyone tuning in again for the next in the webinar series. So the next webinar will be kind of Python related and should be happening in April, kind of mid-April. So just keep your eyes open, and hopefully we'll see you again next time. So thanks again, and thanks, Ray.
Thanks.
Bye.